Okay, let's look at chapter 17 here. Changes in communities. We're getting into some fun stuff here. So, key concepts for this chapter are agents of change act on communities across all temporal and spatial scales. And that succession is the process of change in which species composition over time as a result of both abiotic and biotic agents of change, and that's of particular importance. Experimental work on succession shows that mechanisms to be diverse and context dependent, and communities can follow different successional paths and display alternative stable states, which is another thing I really like. The book starts off with this example of the eruption of Mount St. Helens on May 18th, 1980. And, it was a big disastrous event. People were really unsure of where the long-term impacts are going to be. And, this gave us an example to look at really disturbance on a major scale where massive ecosystems have been just effectively wiped clean in this, where the entire forests were just scorched and blown down. So what had been a big healthy forest was just piles of matchsticks, effectively, and also opened up this whole new ecosystem here, this pumice plain. So just covered all of the old sediment with a whole bunch of new sediment that kind of gave all of these different levels of impact, and then allowed ecologists to track those through time. And generally, the ecological response has been shockingly positive, but this allows us to look at ecological succession in ways that we normally wouldn't. Forestation or deforestation, logging, things like that are much smaller impacts because they're only removing one species typically, right? And then forest fires, the same thing too, that those are extreme, but there are a number of species that are fire adapted. We're here, dumping meters and meters of pumice on top of this surface is arguably a large disturbance. And so scientists started looking at this as a natural experiment where they could document the sequence of biological changes that started soon after the eruption. And much of what's been learned was unexpected and has changed the way we view communities and the persistence of life on Earth. Communities are always changing. Our actions are becoming one of the strongest forces behind community change. And we have an imperfect understanding of the consequences of those actions. Probably the understatement of the year. Humans are messing things up, and we really don't. We have an imperfect understanding of those consequences. Yeah, probably so. Here's an example from the Indian Ocean. So the Indian Ocean has had some of the most vibrant coral reef ecosystems. Those are slowly degrading through ocean acidification. Partially, but the word is coral bleaching. These bleaching events where corals are stressed and reject their zooxanthellae, and ultimately leading to typically their replacement by algal species, which then changes the composition from a very complex three-dimensional environment with a lot of biodiversity to some coral rubble, lots of algae. You can see the water quality is darker here compared to it being bluer here, and generally less biodiversity. And on top of this, low-level anthropogenic change, then you've got these episodic events, tsunamis, etc., that come through, or hurricanes that come through and really impact the systems. And their ability to withstand and recover from that, their resilience, has been slowly degraded by anthropogenic impacts, eutrophication, overfishing, physical disturbance, climate change, etc. So succession is the change in species composition in communities over time. The results from biotic and abiotic factors. Abiotic factors, abiotic, non-biotic, climate, soils, nutrients, water, etc. vary over daily and seasonal and decadal over longer timescales. And this has important implications for community change. The stability of the environment and the way that communities change are intricately linked. Abiotic changes in the Indian Ocean are due to climate change. Higher temperature can cause bleaching. Rising sea levels can reduce light. Ocean acidification can both dissolve skeletons or make it harder to calcify. So what we're looking at is like multiple impacts. And so it's not just maybe the ecosystem can deal with one of these impacts, but when you have cumulative impacts, it starts to erode away at the resilience of the ecosystem. In this case, species can be lost and replaced by more tolerant, like weedy species, which is probably an unfortunate term because in this case it's typically algal species, aka sea weeds. Abiotic agents of change fall into two categories, and this is an important note. Disturbance is always abiotic. If you think of, well, this like deer came in and disturbed the bush by eating it. Well, no, it didn't disturb it. It preyed upon it, right? So we have different words for organism-to-organism interactions, competition, facilitation, etc. Disturbance is an event that injures or kills some individuals and creates the opportunities for others. Here they're saying tsunami, a drift log smashing up against the rocky intertidal, smashing mussels and barnacles is a disturbance event. And so these occur over different scales, both of space and time. And stress are abiotic factors that reduce growth, reproduction, or survival. So temperature stress. So we're talking about stress, meaning the organism's stressed, but it's the abiotic environment that's stressing them. So that's an important distinction. Biotic agents of change include species interaction. So we talked about competition, facilitation, etc. Diseases that impact ecosystems, sea star wasting disease. Ecosystem engineers are keystone species that are coming in or leaving. Again, sea stars, otters, kelp forest, all of these things really help. They're major agents of change. With or without them, environments look a lot different. Biotic and abiotic factors can interact and produce community change. An ecosystem engineer can cause a change in the abiotic conditions that result in species replacement. Nursery tree example, a ecosystem engineer tree comes in, creates shade and cool, more moist environment. Other species move in and then perhaps eventually move into that favorable abiotic environment and perhaps eventually replace that species. We're going to look at the frequency, intensity, and scale of these impacts. And so Mount St. Helens it's not like a worldwide impact, right? Like it is a big impact for that area. It's a reasonably sized impact, but it's not very frequent, right? Like volcanoes are not erupting all the time. And so we can look at this diagram here of comparing frequency and intensity. And so if we have low intensity but high frequency impacts, that's likely not to lead to successional change. It's likely to disturbances that are kind of absorbed in the system. Moderate frequency, moderate intensity can lead to secondary succession, so smaller successions, and then infrequent high events. So this is like knocking it down a succession level. Low frequency, high intensity, volcano exploding will push things back to the primary succession to reboot the system, wipe the slate clean, barren ground, and start with early successional species and then move on to late successional species. Another way, this is called a Stommel diagram, and they're interesting to look at. So this is a Stommel diagram. It's very old. Stommel did this in like the 50s or 60s. So this is three-dimensional plots at the time. And then McGowan redid this. This is in the 70s. McGowan's the lead author of this chapter. And what it's doing is it's putting oceanographic events in time and space. And so we've got the log centimeter scale here. So this is space. Log time, so minutes, days, weeks, months, years, centuries, tens of thousands of years. And so it's a way of thinking about the frequency of events and scale of events. And there's a couple interesting things that are interesting here. So one, this was initially built around oceanography, and then what McGowan, the physical oceanography, and then McGowan added a layer of biological change to it. And so here you see this diel vertical migrations here. So the largest migration on the Earth happens every day, and it's the zooplankton and small fishes in the ocean that come up to the surface of the ocean at night and go down during the day. So there's this massive biomass that's migrating frequently kilometers every day back and down. So it's a massive scale that occurs ocean-wide, worldwide, and it occurs on about a daily scale. And then we can look at micro patches. So this could be small ocean eddies or currents breaking off, all the way up to ice age variations, annual cycles that happen, changes in upwelling annually, things like that. What else? I was thinking about this more from the physical standpoint. So it's kind of interesting to just think about the differences of scales. So like an ice age variation happens over a long time on a large scale, and you can have smaller events that happen on smaller scales. But I like the idea of diel vertical migration being this like worldwide event that happens every day. It's this massive amount of biomass moving. So smaller, more frequent disturbances, such as a tree blowing down, can create patches of resources for one another. And the mosaic of disturbed patches can promote species diversity over time, but might not lead to successional change. So it might not be enough to change the entire forest composition. A few trees blowing down opens up patches, more sunlight hits the forest floor, different low plants will do better there, which will break up the diversity or increase the diversity of the forest, but not fundamentally turn the forest into a grassland. That's what we're talking about there. So succession involves colonization and extinction due to abiotic and biotic agents of change. Theoretically, it progresses through stages to a climax stage, a stable point at which it changes little. There's some argument about whether or not succession will ever lead to a stable end. So it kind of depends on time scale and what you consider stable, right? Like, is it our observations over a few number of years, or is it a longer time scale? So this is a simple model of succession that involves a transition between stages driven by species replacement over time. Theoretically, these changes ultimately result in a climax stage that experiences little changes. There's some argument of whether or not it's a stable point. So you have no life, freshly exploded mountain, the pioneer stage that then moves to an intermediate stage that ultimately leads to a climax stage. You can have a climax stage get knocked back and go back to the secondary succession, and then they're likely to go back to the climax stage. So if we go back and look at these sorts of disturbances, they can knock systems kind of mid-frequency, mid-intensity, can knock systems back to this some life stage, and then they would undergo secondary succession and then drive back to the climax stage. So it's a simplistic model of thinking about, okay, we start with nothing, we've got pioneers, then we've got an intermediate stage, and then we have our sort of like apex, in theory, stable climax stage. If that system is impacted, it kind of sticks in this feedback loop here. But, there's some arguments about that. So we can look at the two primary types of succession, primary and secondary. Primary is the colonization of habitats devoid of life, i.e. Volcanic rock. The Mount St. Helens example, like new sediments moved down. That's previously uninhabited. And the secondary succession, which is the reestablishment of a community in which some but not all of the organisms have been destroyed. Logging could be an example of that, right? Like you go in, you cut down the trees. Not all of them are destroyed. Depending on the severity of fire, the same thing here too. And particularly, fires are very nuanced. And so particularly fires that have been used for like fire management for thousands of years, they would kind of open up areas, but not destroy all of the organisms in that area. So primary succession can be very slow. Initial conditions are unhospitable. So your first colonizers or pioneer or early successional species tend to be stress tolerant, and they transform the habitat in ways that benefit the growth of other species. So you can imagine a new volcanic rock, like in Hawaii, there's lava flowing down, you have this volcanic rock. Early successional species would be able to take hold there, need very little to no soil, and then build up that soil over time, and then other organisms will come in and benefit from that. Secondary succession occurs after fires, storms, logging. The legacy of the pre-existing species and the interactions with colonizing species play a larger role than in primary succession. Primary succession is just whoever can live in this barren habitat will survive. In secondary succession, there's already players in the system, and so they're interacting. This is looking at space for time. This is a pretty interesting concept that is used a lot, and it's this idea of if we want to look at community change takes a long time. It could take on the order of hundreds to thousands of years. And if we want the answer now, we can't just watch a patch of ground, watch our 100 quadrats over 1,000 years. We'll need some other way of trying to figure out how succession happens, these kind of slower, longer, these slower, longer processes. And so here's an example of sand dunes that you have sand building up over time from the ocean, or the ocean dropping as well, which can cause the same sort of thing. And if you imagine you start here at the beach with barren sand and you walk up the hill, you're walking through time. And so the dune, the forward species are really the first ones to establish. They stabilize the environment, keep the sand from moving, more sand builds up. They change the soil from barren sand to having more organic content, maybe more nitrogen, better water holding content with more organics. You get that. You can think of, obviously when we garden, we don't normally garden in just big piles of barren sand. We have nice fluffy organic matter. So you have this buildup of soil quality, stabilization of the environment, and then other things can start to move in until we wind up with a large tree environment that could take hundreds of years to develop, but they can grow tall and shade out all of the earlier species. And so that's kind of our typical forest succession, in this diagram here of going from really dune grasses into large trees. So that's one interesting way of thinking about it. And interestingly, this was done in 1899. So even 2000 was a long time ago now. So what is that, 121 years ago? That's pretty interesting. I cut out a lot of the hero stuff, like, all the ecology books have this person was a hero, this guy was a hero. And I talk about some of them that are my personal heroes. Elton I don't know that much about, but I'm just impressed. He wrote a book at 26 that was impressive, which maybe you'll write a discipline altering book when you're 26, but I didn't. So this was a profound idea at the time, which is the abiotic environment matters, and like these prior conditions will diverge what happens to an area after a disturbance. In this case, it was logging. And so he came up with a system where if you had a pine wood forest before felling, before logging, and the soil was dry, you'd wind up with one type of community. And if the soil was more moist, you could wind up with the sphagnum peat bog. And so even though they both started with the same initial conditions, if you reboot the system, they're going to diverge and potentially go into different directions. And so that was this idea of like interaction with the abiotic environment, that the same system, even though the conditions were the same, they will diverge depending on, in this case, soil moisture. And Elton emphasized that the only way to predict the trajectory of succession was to understand the biological and environmental context in which it occurred. And Elton showed that how animals, by eating, dispersing, trampling, destroying vegetation, could also influence the sequence and timing. So prior to that, it was like plants are doing everything and animals are just these dumb creatures along for the ride. Connell and Slatter. So Connell's Joseph Connell. He's the famous intertidal guy. Reviewed the literature of succession, proposed 3 models. I'm going to talk about them. I'm going to give an example, and then we'll walk through the model that the book provided. But it would be good to be familiar with the examples I'm going to give. And did I get one? Sorry, give me 1 second here. Yeah. Okay. Sorry. There was one example I was trying to find one I really like, and anyway, I have one. So the 3 different like basic models of succession. The first one's facilitation. So this is the idea that early species modify the environment in ways that benefit later species. The sequence of species, the species facilitations leads to the climax community. And so, Clements, was this Clements? Oh, this is Cowles. Okay. And so this is maybe like the way that makes the most sense, which is barren environment. You have some small lichens and mosses that take hold in that barren environment. They start to build up soil over time, and something else comes along, and something else comes along, and eventually, we've got a forest ecosystem. But it took those few early species to establish that soil, where prior it would have been barren sand or rock or something like that. And so these early successional or pioneer species are really important, and they're the ones who set the environment up for the later successional species, ultimately ending in a cedar forest, starting off with bare rock. Like, how do we get from here to there? It's these early successional species that really get the ball rolling and start with things like soil development. There's the tolerance model, which assumes early species modify the environment in neutral ways, neither benefiting nor inhibiting later species. And that's one that is perhaps hard to think of some examples. And we've got one in the barnacle world. But this is where the first one that shows up, they're not in any way benefiting or impeding the next species to show up. So the next species that show up can compete in that environment just fine. The first species that got there is not really inhibiting, blocking out, competing that second species, nor is it really benefiting that second species, nor is it like providing nitrogen or soil composition or moisture or anything. The inhibition model assumes that early species modify conditions in a negative way that hinder later successional species. And so this would be examples of, the first one there kind of takes over and either has allelopathy or some other mechanism to really inhibiting the further succession of other species. but mechanisms driving succession rarely conform to any one model, so there's frequently multiple aspects going on here. And in that spirit of, not everything fits within a nice box, we're going to look at this example from Glacier Bay in Alaska. Now, this is an interesting example because it's combining a few different things we've talked about. One is space for time, and so what we have here is a glacial area where the glaciers receded over a period of 100 plus years. And so with that glacier retreating, we can date that and figure out what that glacier retreat rate's been. So when we walk into an environment, we can say, well, this environment, 150 years ago was under ice, and now it's not. So therefore, we've got a good clock for this environment. So rather than being able to watch one patch of ground for 150 years, now we can just walk up the watershed and look at 150 years worth of succession. And so this gives us the ability to understand some of these forces in play. And I'm going to walk through the facultative effects, and then we'll look through the inhibitory effects. And so facultative effects, so that's the facilitation model, facilitation model. And then the inhibitory effects, that's the inhibition model. So we start with our early pioneer species, mosses, lichens, something like that. Lichens, liverworts, forbs. And then they set up the environment. They have good survivorship. They're taking, in this case, it's not bare rock, it's probably glacial till, so gravel, sand, stuff like that. They're beginning to fix nitrogen, if possible, setting up the soil system. And then dryas come in, which is a small shrub. They have a positive impact on nitrogen and a positive impact on growth. So we go from small lichens to a small shrub species, and then you move into alder. And alder are pretty weedy species that whenever there's recent disturbance, alder tend to pop up right away. If you look, like a housing development's just been cleared, or a bunch of trees have just fallen down, alders typically pop up pretty quickly. And alder are doing a lot for the soil. They have mycorrhizae. They're helping fix nitrogen, and they're can set up the soil system. They've got big root mass. And then coming in later are spruce. And so spruce then are germinating in this mix of dryas and alder. And eventually they're going to grow up and shade out. Some of the alder are going to go away, and some of the dryas might stay behind. And so when you look at, like, if you've got a big alder thicket, that's typically a newer environment, or an environment that's not suitable for the larger species, cedar, things like that, around here. So that each species is kind of playing a role in building up until we get to a spruce-dominated system where the spruce can grow up tall and shade everything out. But it takes 100, 200 years or so for the environment to get to a point where spruce can really take hold. Now, there's also some inhibitory effects here as well. So on the facultation or the facultative effects, both dryas and alders increase soil nitrogen that help the establishment and growth of spruce seedlings. However, dryas and alders also produce leaf litter, which can inhibit germination and survival. So it's kind of a combination there. So if a spruce does, if it's able to germinate and grow up above the leaf litter, then it tends to do quite well. So there's also competition for roots, for lights, competition for nitrogen. So in this model, there's no free lunch. That it's not everybody's just yay spruce, we're going to help you out. There's some negative impacts as well. And then we can look at the Glacier Bay example again, and look at the succession stages in pioneer, dryas, alder, or spruce, and the amount of, that should be soil nitrogen. Oh, I said soil nitrogen. Soil nitrogen, and it's increasing through time. And so with each successional changes, the soil nitrogen is a proxy really for soil development. You can think of sterile sand and gravel that the moss and lichens are establishing in, but over time it starts to build up and get more organic content, and likewise get more nitrogen content. Here's another look at facilitation. Second here. The facilitation. So this is an interesting one. So this is a study. This is, I didn't put it in here. Oh, that's Farrell. Okay, sorry. I thought it was Connell for a second. This is looking at algal density as a function of barnacle presence. And so here the control is with barnacles, how much algae do we have? And then when we remove the barnacles, how much algae is there? And what they're making an argument here for is when you've got a bare piece of rock in the ocean, when barnacles come and settle on that rock, then they are facilitating algae to come in as well. So algae stick better to barnacle tests. Barnacles live fast and die young, so they're always leaving tests behind. But they're also providing substrate for these for the algae to stick to. And so if we remove barnacles, then the algae doesn't come in and colonize the area. So in this case, barnacles are first. They set up the habitat. They provide substrate for the algae to live on. The intertidal examples are used pretty frequently because things happen so fast. You don't have to wait 200 years for something to go from bare ground to a healthy ecosystem in the ocean. That'll happen in a year or two. So we see a lot of intertidal examples for classic ecology because they're small experimental units. You can do it at the meter squared. You can take a 1 meter through 3 foot by 3 foot, transect or quadra out and scrape everything off and see what happens over time. It's harder to do that in the Olympic rainforest, for example. So here, barnacles come in first. They set up the environment. Algae sticks to them. And in that way, barnacles are facilitating the growth of algae. Tolerance. So this is back to now this says Balanus, and I often say Balanus because semi-Balanus was Balanus for a long time. And so all the old literature has Balanus. I don't remember when it changed. I mean, yeah, it was a while ago, but not that long ago. Okay, so when it says Balanus here, just read semi-Balanus. So we're back to the thalamus, semi-Balanus story. What else can we do with these two critters? Well, one thing we can do is look at the colonization or the recruitment of Balanus on rocks, semi-Balanus on rocks that already have thalamus. And so if thalamus comes in first and coats the bottom of coats the rock, semi-Balanus will come in and recruit just fine. The presence of thalamus does not impact the recruitment of semi-Balanus. That's shown here where there's maybe a slight improvement. This is thalamus removed, and this is the control, which is thalamus present. There's effectively no change or no significant change for the amount of Balanus, I keep saying Balanus, man, semi-Balanus cover or semi-Balanus density on rocks that have thalamus versus having thalamus removed. Semi-Balanus doesn't care about thalamus. They did the experiment in reverse, and thalamus settles less when semi-Balanus is there. So it's not a two-way relationship. But for this purposes, this is an example of tolerance. Semi-Balanus, if they're the second wave species, they're not impacted by the presence of thalamus there prior. And as we know, they'll eventually just overgrow and outcompete thalamus as well. This is a look at inhibition. And so this is the model that assumes early species modify conditions in negative ways to hinder later successional species. And so this is another type of marine algae. What we see here is when you look at the recruitment and presence of this algal species compared to ulva is like sea lettuce. When sea lettuce is present, this species cannot really come in. So ulva takes over, and ulva inhibits the growth of the other algal species. It's hard to read sideways. It's chondracthinus. I should look up a picture of it. Chondracthinus. I don't know chondracthinus off the top of my head. I know ulva's sea lettuce. It's like the seaweed you see everywhere. It's the flat, sort of like 1 or 2 cell thick, like long sheet kind of one you see in like muddy areas. And then when we remove ulva, the other algal species can come in quite easily. So when ulva's there, it inhibits the growth of other algal species. It typically does this by being large and flat and covering up all of the substrate. So even if new algae were to recruit in the system and get hold, they're light limited. So ulva outcompetes them typically in the light space. So we're going to walk through the model here. And so we've got our facilitation model. In all 3 models, or I guess not really an inhibition, but disturbance is opening up a new area, creating opportunities for colonization. In the facilitation model, the species arrive in the open habitat early. They establish themselves. The early colonists modify the environment so it's less suitable for their species, and then ultimately becomes more suitable for the next wave of colonization, the next wave of succession. The growth and maturity of juveniles of late succession species is facilitated by the environmental modifications from the earlier ones. So again, like moss lichens show up, they're good in this dry environment, and eventually they, not on purpose, but eventually a bunch of soil builds up from them, dying, decaying, things being trapped within them, and then they don't grow well in that soil, but other species do. And the sequence continues until the resident species no longer facilitate colonization or growth of other species. In the forest ecosystems, typically ends with like large, around here, large cedar trees that then dominate the environment via shading. The tolerance model, early colonists modify the environment so it becomes less suitable for subsequent colonization by other early species, but the modification has little to no effect on subsequent colonization by late successional species. Juveniles of later successional species that colonize are already present, grow to maturity, and the sequence continues until there's no species can colonize the area. So we get to, again, some apex environment that in theory may be stable. Sorry, I was just trying to look something up real quick here. To our climax species. And then the inhibition model, early colonists modify the environment so it becomes less suitable for subsequent colonization by both early and late successional species. And as long as individuals of the early successional species persist, they exclude or suppress subsequent colonists. So they come in, take over, and prevent the growth of other species, and typically would take another disturbance events to kind of bump this out of the inhibition model to maybe letting either facilitation or tolerance model take place. So you need to get a couple other species in there that can start competing with these early colonists that have really dominated the environment and prevented the recruitment of new species. Okay, I'll end it there, and we'll come back for the next sections.